Hi, ladies and gentlemen. Welcome to Lesson 18. So this is the beginning of Chapter 4. The point of Chapter 4, the main topic is orthogonality. And we're going to take a look at what the orthogonality means, how we can generate orthogonality in the case where we don't have it, and we will also look at solving systems of equations that are overdetermined instead of underdetermined. All of that to come. So let's start out here. The first thing that I want to emphasize is this is Strang's comment at the end of chapter 4. He talks about the victory of orthogonality. It is impossible for us to state just how important orthogonality is when we're talking about vector spaces. What it provides for us, the special things that we can do when we have vectors or subspaces that are orthogonal are one of those things that we take for granted. And so we're going to start to peel back the layers a little bit here in chapter 4 to really identify the critical nature of orthogonal vectors. Let me just remind you, you're already accustomed to this. We talked about it previously, but if I have the vector 3, 2, negative 5, this is really 3i hat plus 2j hat minus 5k hat. And in no small part, it's very easy to determine what the vector of coefficients is for the very simple reason that we have a basis in R3 that is orthogonal. And we will, as we work through for the next couple of chapters, actually through the rest of the course, because this impacts the eigenvalues and eigenvectors as well as the singular values and singular vectors, we will look at the importance of having orthogonal functions. First things first, let's take a look at what Strang tells us. The definition of orthogonality, it's exactly the same as we talked about previously. We're just going to use the dot product to look to see if that's equal to 0. If it is, we have orthogonal vectors. There's a little bit more information which we will cover when it comes to the Pythagorean theorem type of thing. What we want to do, though, is we want to realize that we have a concept of orthogonality for subspaces. So not just for vectors, but for entire subspaces. And we're going to dig into this a little bit more as we have conversations today. We also want to take a look at projection. That's very important. That's going to be section 4.2. We'll talk about that next lesson. And then we'll talk about least squares. This is the situation where we're trying to solve a system of equations that is overdetermined. And he says that here, ax equals b is unsolvable. We have a system where we have more constraints than we have degrees of freedom. And so we can't actually come up with a solution, but we can approximate and we can build models. This is the kind of thing that you've seen and participated in probably in other courses. And we're going to provide you some structure with that. We're going to spend 2 lessons on that material. And then finally, what we're going to do is we're going to take a look at Gram-Schmidt orthogonalization. So the Gram-Schmidt orthogonalization actually leads us to a decomposition. This will be our third decomposition. Remember, we did A equals CR, where R is really the RREF without the 0 rows. And then the C's, the vectors in C are the independent vectors that are in the columns of A. We also looked at A equals LU, and this was the process of Gaussian elimination. We execute Gaussian elimination, we come up with this decomposition, and it has some advantages for us. Primarily, the ease with which we can construct the L matrix given the elimination that we're doing. This is our third decomposition, and it is nothing more than the result of performing Gram-Schmidt orthogonalization. This is section 4.4. This will be the last section that we cover in chapter 4. It is, and I just want to highlight this, this is one of the things that Strang notes here, right? In many ways, the A equals QR decomposition is more valuable to us than the LU decomposition. It gets used for a lot more things internal to the computations that are done within a computer when we're doing numerical linear algebra. So when MATLAB is running code behind the scenes to help us out, it is doing a lot more QR decompositions than it is LU decompositions. And we'll talk more about that later. So let's get started then with the orthogonality of vectors and subspaces. And really, again, you are familiar with what it means to be orthogonal. There's also this relatively straightforward result which follows directly from the Pythagorean theorem. I'll draw a quick picture, but it's obvious. If I have two vectors that are orthogonal to one another, all this is saying is if I take the sum of those two vectors, so I want to add these vectors together, well, remember pictorially, if we're going to add, we link them together and the sum is right here. So the sum of the vectors is this thing here. But that's just the hypotenuse of a right triangle. And so it makes perfect sense that the magnitude of that sum vector is equal to, when it gets squared, is equal to the squares of each of the vectors we use to build it. And that's all he's saying right here. Whoop, let me change over here. That's all he's saying here is the Pythagorean theorem is giving us this thing as well. So the piece that I do want to briefly talk about while we're in the introductory part here is subspaces are orthogonal. So let me get this out of our way. Subspaces are orthogonal when all of the vectors in each subspace is orthogonal to all the other vectors in the other subspace. So a quick graphic, right? Let's say we had a plane in R3. We know that a plane, all the vectors that are in that plane, that is a subspace. That is a two-dimensional subspace in R3. That leaves us one dimension left over. And we'll see this, I'll show you a MATLAB demo, but you can well imagine that that remaining subspace is actually perpendicular here, okay? And so what we have is we have a two-dimensional subspace in R3 and we have a one-dimensional subspace in R3, and those subspaces are orthogonal because every vector that's in this one-dimensional subspace is orthogonal to all the vectors that are in the plane. And similarly, every vector that's in the plane, no matter which vector I select, all of these vectors are orthogonal to the other vectors in the one-dimensional subspace. That's what it means to be orthogonal subspaces. There's a little bit more here. This is the Pythagorean theorem piece of it. And now comes one of the just staggering items. It's obvious. Let me just lay it out here for you. He says the null space of A is orthogonal to the row space of A. The null space of A, given a matrix A, vectors that are in the null space, these vectors are orthogonal to the rows of A. Of course they are. They have to be, right? This is the amazing result. Let's bring this to the front. This is the crazy thing. On each side of the picture that we have, right? So on this picture here, the reason it's drawn the way it is, the reason it's not drawn using the clouds that I showed you initially, is because these subspaces are orthogonal to each other. All the vectors that are in the row space, that's here, this is the column space of A transpose, are orthogonal to all the vectors. They are orthogonal subspaces. Similarly, these are orthogonal. All the vectors in the column space are orthogonal to all the vectors in the left null space. Fundamentally important to us, and we'll see why when we take a look at an example coming up in a little bit. This result is staggering. Make sure you read through all of this content because there's good information here as he talks through and kind of explains why these subspaces are orthogonal to one another. It continues on down here. He continues the conversation talking about the column space and the left null space. So we leave that for you to read. Then what he does is he has a conversation about orthogonal complements. This is another really important idea. The orthogonal complement is written as the script, for example, V, with a perpendicular is the superscript. And it contains all the vectors. This is what he says. The orthogonal complement V perpendicular of V contains all the vectors that are orthogonal to V. So every vector that's in the orthogonal complement here, that is the set of vectors that are orthogonal. Let me give you an example, and I just want to show you in MATLAB. Let me pull it up. All right, so if you remember early on, we took a look at linear combinations. These are the red and green vectors that I have shown here. And what we want to do is we want to take a look at all of the linear combinations. And we already know what we're going to end up with. We're going to end up with, as long as the vectors are linearly independent, which they are, we're going to end up with this plane here in R3. So the vectors are in R3 and all the possible linear combinations, the span is in R3. But what this leaves us is the orthogonality of the other subspace. This is the orthogonal complement. This blue vector represents the subspace that is orthogonal to the span of these two items here. And so we'd like to be able to better understand what this is representing. I have a picture of it here. This is the fundamental subspace right here. Sorry. All right, so sorry about that. So what we have here is we have the span of the two vectors, which is this plane, and then we have this blue vector here. And the blue vector is actually the vector 2, 11, 5. So the span of that vector is the subspace here, right? So the subspace is the line that is in this direction, and it is the orthogonal complement. This is the orthogonal complement to the plane that we see. And we can verify this. So let me delete that out of the way. Taking a look at this, if we take the dot product of this blue vector with either the red vector or the green vector, we can see that we end up with 0. That's the definition of orthogonal complement. It's all the vectors that are in the space that are orthogonal to whatever subspace we're talking about. It's really a way that we can take a vector space and break it into two different subspaces. One thing you'll notice with the picture, and I'll pull this back up. One thing you'll notice with this picture is we are limited. We have our subspace, which is the plane, is two-dimensional. What is the maximum dimension of a plane that could be an orthogonal complement? Yeah, it can't be 2. We can't come up with another plane that fits in here and makes an orthogonal complement. Some of the vectors would be orthogonal, but not all the vectors. So we are actually limited to a one-dimensional orthogonal complement. We can't have anything more than that. And that's one of the really important results that Strang talks about here, is the fact that we are limited in the dimensionality of what we can have for these orthogonal complements. So he makes this big point right here. He calls it the fundamental theorem of linear algebra part 2. This is more important than the first part that he talked about. The fact that it really is mind-blowing that the row space and the null space are orthogonal complements. They cover all of Rn, and they are orthogonal. All the vectors in one are orthogonal to all the vectors in the other, and that's true with the column space and the left null space. Let's take a look at what this actually means for the solutions. He's drawn this picture here, which is close to the picture that's on the cover of his book. This is so important. But what I want to do is I want to take a look at the solution for this problem so that we can better understand what it is that is so important about this. So this is a simple setup here. We know what we're going to do to solve this. We're going to build the augmented matrix and we're going to RREF it. Let me write down what that RREF matrix is. And now, what do we gather from the RREF? Well, it's important to remember this is the RREF for the A matrix. So we can gather information about the A matrix itself, and we will do that, and we will put that information into this diagram just to establish the point that he's making over here. But first of all, I want to come up with a solution. So we can write out the solution. We'll go through this the way we always do. This is x1 minus 2x3 is equal to 5, and x2 plus x3 is equal to negative 4, and of course x3 is the free variable. It's equal to x3. And so the full solution here, let me just write it down, x vector, which is equal to x1, x2, x3, is equal to 5, negative 4, 0, plus x3 times, and then we have the 2, negative 1, 1. And that is, you remember, this is the basis for the null space. Let me scoot this up a little bit so it's out of my hat. So this is going to provide us the basis with the null space. What he's saying over here is that every solution to the problem that we're looking at has two pieces. It has the particular solution that we talked about here, and it has the null space solution, which in this case is the special solution that we've talked about earlier in chapter 3. And he is now calling this XR, referencing the fact that it's in the row space. So we have a vector, and this is the critical nature of the conversation. We have a vector that exists over here somewhere. And because the null space and the row space are orthogonal complements, we can decompose the solution vector into some part that's in the null space over here. This is the xn portion for some x3 value that we choose. Let's just say we choose it to be 1 for right now. And we have this component over here, which he calls XR, which is really the particular solution. It's in the row space. And if we pick x3 to be 1, we get the solution to be 7, negative 5, 1. The vector 7, negative 5, 1 can be decomposed into 5, negative 4, 0, which is the component that we see over in the row space, plus the 2, negative 1, 1. And his point is, and the graphic is a little bit light over here, which is why I want to make this point, we actually have an infinite number of solutions which are represented in his picture in the following way. Any vector that touches along this line, and the line really kind of starts here and goes out, considering his picture, all of these vectors are solutions because their projection into the row space is exactly what we need to solve the problem. All the pieces that are in the null space, when we do a projection into the row space, go away. The reason they go away is because the row space and the null space are orthogonal complements. They're orthogonal vector spaces. So the pieces that are in the two separate spaces can be compressed down to 0 using projections, which is the conversation for next lesson. It's extremely important idea for us. Where we're headed in section 4.3 is when we're trying to solve a system, let me write one down, just something like AX equals B, where B is not in the column space. Well, given the picture that we have, what is that going to look like? That's going to mean that we have, and I'll switch over to green, it means that we're going to have some B like this. Some B vector that's not in the column space of A. It's going to have a component over here, which is going to be in the left null space. So it's a problem we can't solve. There is no X in the input space that will map to that B, because that B is not in the column space. But because the column space and the left null space are orthogonal, we will be able to project the B into the column space, which gives us a problem that we can then solve. That's where we're headed with all of this as we move towards section 4.3. That's the conversation he's having in here. One really important conversation is the fact that internal to every matrix, we can find an R by R. Remember, R is his representation for rank. We can find an R by R invertible matrix in the center of my linear mapping, my linear operator, which is represented by a matrix. Inside of that, even if that is singular, inside of it, there is a portion that is non-singular. There's a portion that's invertible. And we'll talk more about this. We don't cover the pseudo inverse in section 4.5. We will address it later when we're talking about singular value decomposition. But it's important to realize that even when I have a singular linear operator, it contains some component, some aspect that is invertible. More on that later. All right, so this last piece here, combining bases of subspaces, this is really a repetition of, and perhaps you remember this, it's a repetition of the following are equivalent. So we talked about this when we went through these questions. I've just copied this out of the participation questions we went through. And this is the following are equivalent, which means if any one of these statements is true, they're all true. The following are equivalent. And we often abbreviate that as TFAE, the following are equivalent. So what is it? We're always talking about square matrices now. And if the square matrix is invertible, then all of the following things are true. And that's really what he's getting at with all of this conversation here. He's talking about the representation of the columns as a basis for Rn, which we have right here. The columns are linearly independent. We know that Ax equals B has a solution, and moreover, we know that that solution is unique. And we know it's unique because the null space of A is trivial. So we hadn't talked about null space when we were talking about this, but that's worth adding in here. The null space of A is equal to 0. The only thing that's in the null space is the 0 vector. That's part of his conversation. This is something that is fundamental to understanding linear algebra and how all the different things that we've been talking about tie together. You want to make sure to read through this probably a couple of times, make sure you take some notes and that you have this down. Again, it only applies to square matrices, but it's very important to how we are actually doing the information and where we are going with respect to particularly solving Ax equals B. So solving the Ax equals B problem, we understand when we have a non-trivial null space that we have an infinite number of solutions if we have one solution that exists. As I said previously, where we're headed here is for overdetermined, where we don't have any solution. And then finally, there's this conversation down here, this set of examples 3 and 4, and you definitely want to work through these and understand them. You want to understand that, and I'll just give you one indication. If we have a 5-dimensional space and we have a plane in that 5-dimensional space, so we have a 2-dimensional subspace of R5. So this is not R2, right? This is absolutely not R2, not R2. It is a 2-dimensional subspace of R5 vectors. Then what is the orthogonal complement? If we call this plane, this vector space W, then the question is, what is the orthogonal complement? It's all the other vectors in R5 that are orthogonal to the plane. I can't draw you the picture. We can't see in R5. But what we do understand is the orthogonal complement has a dimension that must be equal to 3, because there are 3 dimensions left in R5 that haven't been covered by the 2-dimensional plane. That's going to help you answer the questions here in example number 4. All right, let's take a look at the problems that we have for today. These are the participation questions having to do with orthogonal complements, of course, having to do with understanding how this influences. I'm using his notation here, where the B vector, in this case, I'm talking about B vectors instead of solutions, has some component that is in the row space and some component that's in the null space. So now I'm not talking about the solution to AX equals B, I'm just talking about some generic B vector that happens to be in the input space of my linear operator. And then here we're looking at how can we fill out R3. We're missing a vector from R3 here. How can we fill out R3? Thanks very much, and we look forward to seeing you in class.